Hey, welcome to today's CyLab seminar. Today we have Anupam Datta, who's going to be presenting on privacy and accountability. So Anupam is an associate professor at Carnegie Mellon University, where he holds a joint appointment in the computer science and electrical and computer engineering departments, in addition to here at CyLab. Just a few words about his research. His research focuses on the scientific foundations of security and privacy. Anupam's work has led to principles for securely composing cryptographic protocols and software systems, and applications of those principles have influenced several IEEE and IETF standards. His work on privacy protection has led to formalizations of privacy as contextual integrity and purpose restrictions on information use, accountability mechanisms for privacy protections, and their applications in healthcare and web privacy. So please join me in welcoming Anupam for his talk today.
Thank you. I want to talk today about some work that we have been doing here at CMU over the last 6 years or so on trying to understand what privacy means in computational terms and developing algorithms and computer systems for their enforcement. That's why the subtitle Computer Science Perspective, Privacy and Accountability, these are topics traditionally studied by legal scholars and philosophers, but now we live in a world where personal information is everywhere. And in this world, it has become particularly important for computer scientists and engineers to start working on this problem. If you think about the world we live in today, personal information, huge volumes of personal information are hoarded by a whole bunch of companies like the ones we have on this slide. Google knows what time I wake up and what time I go to sleep. Facebook knows who my friends are and what they like and dislike. Amazon knows what books I read and what DVDs my wife watches. Apple knows where I am most of the time, and my bank wishes me happy birthday. Now, this is a brave new world, and with the advent of this wide-scale sharing of personal information, we have seen the emergence of a lot of useful services. At the same time, it raises a huge host of privacy concerns. And that's the central research challenge that I want to address in this talk. How can we as computer scientists help ensure that organizations, like the ones on the previous slide, the programs and the people in those organizations, respect our privacy expectations in the collection, use, and disclosure of personal information? To make things a little more concrete, I want to give you some examples of privacy policies in the web privacy domain and in the healthcare privacy domain, and this will motivate some of the technical development I'll talk about today. So in the web privacy space, think of web search engines like Bing or Google, and if you look at their privacy policies, you'll see examples of policies like the ones I have on this slide. For example, Bing promises not to use detailed location information, such as the full IP address for advertising. Part of the concern here is that there might be too much location-based discrimination. Similarly, Google promises not to use race for advertising. And we're interested in checking that the implementations of these systems, perhaps as checked by an internal auditor, someone who has access to the source code, respects these kinds of policies. We are also interested in checking that these policies are respected from the outside using an external auditor who may not have access to the internal implementation, the source code, but may be able to interact with Google or Bing over the network from the outside and still be able to check whether these kinds of policies are violated or not. So that's the web privacy setting, and here it's programs that we are primarily interested in checking, that programs respect privacy policies. In the healthcare privacy setting, we have similar privacy policies. For example, if you look at the healthcare privacy law, there is a requirement that hospitals and other healthcare organizations should use patient health information only for purposes like treatment and payment and operations. Similarly, there are clauses where it is okay to share patient health information with law enforcement if there is reasonable evidence of a crime. So in this setting, imagine a patient who comes to the hospital, shares their personal information with the hospital with the expectation that it'll be used in compliance with these kinds of policies. A physician might get access to this information, then share it internally within the organization with the expectation that the nurse would use the information again for treatment. But if the nurse turns around, sells that patient information to a drug company who then uses that information for marketing, then a privacy violation would have happened. One thing to notice here is that the threats here are from authorized insiders, people inside the organization who have a legitimate reason to have access to this personal information, but who might abuse that right to use this information in ways that violate privacy expectations. So we do not expect traditional preventive mechanisms like access control and information flow control to be sufficient for protecting privacy. So these mechanisms will be necessary, of course, to keep outsiders out, to ensure that random people don't get access to our health records, that only authorized people do, but it won't be sufficient. And even in this domain, we have seen the emergence of auditing mechanisms, auditors who examine the accesses to personal information and the sharing of personal information that has been done within and across organizational boundaries to ensure that privacy expectations are respected. And what we would like to do is develop tools, computational tools that these kinds of auditors can employ to show compliance or detect violations of privacy policies. More broadly, there is an interesting and emerging research area here on formalizing privacy policies, meaning giving precise definitions or semantics to the kinds of privacy concepts we see in these kinds of practical policies. Often they impose certain kinds of restrictions on personal information flow, and as we go along, I'll give you concrete examples of what these policies look like. And then enforcement of privacy policies, which what I'm going to focus on are mechanisms based on accountability, audit mechanisms for detection of violations, blame assignment when violations are detected. Resource allocation becomes central in audit because the auditors typically cannot look at everything, and appropriate punishments. So what you see here is very much mirroring what goes on in the physical world in law and order. We have a constitution, a set of laws that we expect people to follow, but the enforcement regime is often not just based on preventive mechanisms, it's based on a combination of detection and accountability, right? And cars, we have a speeding limit, for example, for cars, but the way that that speed limit is enforced is not by designing cars that cannot go faster than the speed limit, but by having cops hiding behind bushes and giving people tickets when they exceed the speed limit. So that's very much the analogy that we will follow in the digital world for privacy protection. So in today's talk, I want to focus primarily on detection. We have some ongoing work on the other pieces of the accountability puzzle as well. And I'll begin by focusing on the healthcare domain and talk about two technical results in this space, and then, time permitting, I'll transition to web privacy and again give you a sense of two interesting recent results. So let's look at a concrete example from healthcare privacy policies. This is an example from the HIPAA Privacy Rule. It says a covered entity, that's a hospital, may disclose an individual's protected health information to law enforcement officials for the purpose of identifying an individual if the individual made a statement admitting participating in a violent crime that the covered entity believes may have caused serious physical harm to the victim. All right, quite a mouthful. And if this gets you all unsettled, there is 85 other such clauses in the HIPAA Privacy Rule, and it's beginning to get at the complexity of the nature of these policies and why we need algorithmic support, tool support for their enforcement. So what I want to do is not to read this. The only reason I picked this example is that it shows a bunch of concepts that arise across the board in privacy policies. It helps me motivate the technical development. So let's start parsing and figuring out the concepts, focusing on the concepts in this example. First of all, often in privacy policies, we will see actions that involve operating on personal information. In this example, it's a disclosure action, a send action that goes from some agent P1 to another agent P2, containing some message M. Often agents are going to be organized into roles. The recipient of the message, P2, is in the role of law enforcement in this example. The policy governs a certain type of personal information, protected health information in this case, and often there is an understanding of what that type is. For example, prescription might be protected health information. We often see temporal conditions in privacy policies. So in this example, the temporal condition was saying that in the past a certain kind of statement was made. Similar examples of temporal conditions are things like consent. For example, if in the past the patient gave consent, then certain types of disclosure may be permitted. Notice is another example which says that in the case of a breach within a certain amount of time, the organization has to inform the consumer that a breach has occurred. Temporal constraints provide a natural abstraction for this whole class of privacy idioms. And then we begin to see concepts like purposes. In this case, the disclosure was allowed for the purpose of identifying criminal activity and beliefs. In this case, you see that there was, for the disclosure to be legitimate, the hospital must have believed that a serious physical harm was caused to the victim. So what I'm going to do is separate out these concepts into what I'm going to call black and white concepts, where the meaning of these predicates are relatively obvious. And there will be other challenges with enforcement, but it's not a definitional challenge. The gray concepts, on the other hand, are hard to define even. What does it even mean for an action to be only for a purpose? So there is, in addition, a definitional challenge in defining what these concepts mean, and that those definitions will then be used as the basis for enforcement. So at a high level, the division of detection of privacy violations will follow this separation. We'll start from the privacy policy as written in natural language. This could be things like the HIPAA Privacy Rule and the Gramm-Leach-Bliley Act for financial institutions. And we have done a first complete formalization of these laws. We translate them into a computer-readable privacy policy, and then we submit it to the audit box. The audit box takes as input the privacy policy written in a form that an algorithm can understand, and the organizational audit log, which records what actions were done by what agents on what type of information. And then the output of this box is that, yes, the policy was satisfied, or that, no, it was not, and here's a violation, and possibly some explanation for the violation. And inside this audit box, mirroring the separation of the black and white concepts and the gray concepts, what we will see are two different classes of algorithms. An automated audit algorithm for the black and white policy concepts. This is fully automated. And then oracles that help us audit these gray policy concepts. And these oracles are tricky to design. They are pretty much like the oracle from the Matrix. We are trying to design a program that's designed to investigate the human psyche, to figure out whether the action was done to achieve a certain purpose or not. And we'll see that while we can't quite build the oracle from the Matrix yet, we try to approximate it with some ideas from artificial intelligence. Okay, so the first thing I want to discuss is this algorithm for auditing black and white concepts. And one of the key challenges for this setting is that audit logs tend to be incomplete, meaning that they may not have enough information to make a full determination about whether the policy was satisfied or violated. And there are several sources of incompleteness. They clearly only contain information up to the present moment, so there isn't information about the future, and yet information about the future may be relevant for making determinations about whether the policy is satisfied or not, especially when we have policies that say that certain things have to happen within a certain amount of time in the future, like the data breach notification clauses. Subjective information, they may not understand. There may not be enough information to decide whether the purposes or beliefs in the policies are satisfied or not. And even if there is information, this algorithm may not be able to understand that information well enough to use it for enforcement. Sometimes logs might be spatially distributed and inaccessible to the audit algorithm, or even encrypted. And that's something that shows up quite a bit in settings where the auditor himself may not be trusted with the entire audit log. So what we want to do is deal with this incompleteness in a graceful manner, not to just throw up our hands and say, well, the audit log is incomplete, we can't make a determination, but to deal with it in a graceful manner, and that's what I'm going to show you. What I'm going to do here is to abstract this form of incompleteness by modeling incomplete logs as three-valued structures, meaning that given a predicate, the log might tell us that yes, the predicate is true on the log, or that no, it's false on the log, or that it's unknown, meaning that there isn't enough information in the log, or the algorithm doesn't understand the information well enough to make a determination. And this third value, the unknown value, which is atypical in treatments of logic, is what will help us deal with incompleteness. So the iterative algorithm for auditing that I will give you a short glimpse of is what we call reduce. Reduce takes as input the audit log L in this slide and the policy phi, which could be the HIPAA privacy rule. And instead of always coming back with a yes-no answer, it'll check as much of the policy as it possibly can, given the information in the log that it understands. And then it outputs a residual policy phi prime, which will be checked when the log is augmented with additional information. So visually, you should think of reduce as taking as input the audit log, and the policy phi naught here could be a formalization of the HIPAA privacy rule, and then it outchecks as much of the policy as it can and outputs the residual policy phi 1. And then the log, when the log is augmented with additional information, you see the log grows here, then you run the algorithm again on the augmented log, and maybe more of the residual policy is now automatically checkable by reduce, and the remaining policy still lives on. And at any point during this process, reduce might take as input additional input from these oracles that help resolve whether the gray predicates like purposes and beliefs are true or false. And that will help resolve the part of the policy that it itself that cannot automatically enforce. So let's get a little bit more into technical detail, and this is for people who have some background in logic. I'm going to go over it rather quickly and talk offline with people who are interested. So we are going to express policies, privacy policies, in a fragment of first-order logic. And the technical challenge, from an expressivity standpoint, this is expressive enough to specify policies like the HIPAA privacy rule, the Gramm-Leach-Bliley Act, and so forth. The interesting challenge from an enforcement standpoint is once we go to this kind of first-order logic, we have quantification over infinite domains, for example, the set of all messages in the English language, and that becomes a technical challenge for enforcement. So returning to our running example, if we take this policy from the HIPAA privacy rule and specify it in this fragment of first-order logic, it looks a little bit like this. I don't necessarily want you to parse everything that's on this slide. The important things to notice is that there is universal quantification here for all principals P1, P2, and messages M, and this is one of the reasons why this is an infinite set. You can write a whole bunch of messages in the English language. And then the black parts, the predicates which are marked in black are what I was previously calling black and white predicates. These are things like a message was sent, someone is in a certain role, a message was tagged with a certain type of information, and so forth. And those are the parts that can be automatically checked by this algorithm. And then the red parts are the gray concepts, and those are the predicates that this algorithm will not be able to automatically check. Let's look at the algorithm in a little bit more detail. Recall that it takes as input a log L and a formula phi. In this case, the formula is simply a single predicate like a send or an enroll. And the algorithm will return true if the log says that this predicate is true. It will return false if the log says that the predicate is false. And it returns unknown if it returns the whole predicate if the log says that I don't know whether this predicate is true or false. So that's the base case of the algorithm. And then it proceeds recursively. So if the policy is a conjunction of two predicates, then we just run reduce on the two conjuncts and take the conjunct. The interesting case is this case of universal quantification. Now, one way to think about universal quantification is to replace it by a conjunction, right? So instead of when you take for all x phi's, imagine that x is for all messages of the English language, then you can replace that by phi with x replaced by the first message of the English language, and phi with the second message of the English language, and so forth. But then what you will end up with is an infinite conjunction. If you just try to apply the conjunction rule on that, then this infinite conjunction will never terminate. So we have to do something more clever. And what we are going to do is restrict the syntax to only have this kind of guard, where the C is satisfied only by a finite number of x's, meaning that notice that while the way the previous policy was written, it applied to all the messages of the English language. But HIPAA, or any other privacy policy for that matter, doesn't really care about all messages of the English language. It only cares about those messages that were sent by the hospital, right? So if the hospital sent a message, then that message has to be in compliance with all those 85 rules. So the guard here, the C in this picture, will have to be expressive enough to capture these kinds of conditions. And then they will be satisfied only by the finite number of instances that were sent out by the hospital. And once you have that, then this can be replaced by a finite conjunction where each one of these psi1 through psi-n are the substitutions of the formula for which makes C true, and this psi prime is allowing for the possibility that in the future, because the log is incomplete, new substitutions might show up. Writing it all formally in Greek font might seem scary, but it's expressing a relatively simple idea. And we have a general theorem which says that if the initial policy passes a syntactic mode check, an idea from logic programming, then finite substitutions can be computed, meaning that this algorithm will always terminate for a certain class of policies which satisfy the syntactic condition. The details of the syntactic condition, I'm happy to talk with you offline. The interesting thing from a practice standpoint is that the entire HIPAA and Gramm-Leach-Bliley privacy rules pass the syntactic check, meaning that the algorithm, which makes use of these technical ideas from logic programming and model checking, actually applies to interesting privacy regulations. And having the generality is nice because the algorithm is now not only restricted to these two laws, it can apply to any policy that falls within a certain syntactic class. So returning to our example, recall that this was our example from the HIPAA privacy rule, and if the log looks like this, when you give the log and the policy as input to the algorithm will run through trying to find substitutions for the universal quantifiers in the log. And on the right, I'm showing you the substitutions for this particular log. So if you look at one predicate, for example, send, P1 matches the send in the log that says that the sender was the UPMC hospital, the recipient P2 was the Allegheny police, and the message M is this concrete message M2, and so forth. Once these substitutions are found, then it becomes a finite conjunction which can be evaluated. And in fact, the log now has enough information to evaluate all the black and white concepts to true, and the residual policy only has these gray concepts marked in red about purposes and beliefs and so forth. So this is how this algorithm proceeds. And when the log, these kinds of predicates, the gray predicates could then be evaluated using the oracles, which I'll talk about shortly. Now we have done an implementation and case study over simulated audit logs for compliance with all the 84 disclosure-related clauses of the HIPAA privacy rule. And there are two metrics that we used for evaluation. One is performance. Does it work relatively fast? And this numbers show that for 15 megabyte log, the average time for checking compliance of each disclosure of protected health information was about 0.12 seconds. The second metric is, does the automated enforcement actually help? So there is a degenerate case of reduce in which the algorithm isn't able to check anything at all interesting about the policy, where the residual policy is the entire input policy. And that would be a spectacularly useless algorithm because it's not really helping with enforcement. But interestingly, for HIPAA, about 80% of the atomic predicates are the black and white predicates, meaning that about 80% of the law, roughly, can be automatically enforced using this algorithm. Yeah, so that's progress, but we still have purposes and beliefs which we don't know which this algorithm will not be able to enforce, which will live on in the residual policy. And we have some ongoing transition efforts on integrating this algorithm into a health information exchange system that's being built jointly with UIUC and the Illinois HLN, and some ongoing conversations with semantic research. Some of the distinguishing characteristics of this work is the general treatment of incompleteness in audit logs, dealing with quantification over infinite domains, and the first complete formalization of the HIPAA privacy rule and Gramm-Leach-Bliley, and some of our nearest neighbors at ETH and Stanford and MIT, who are also motivated by other applications, are missing at least some of these elements. Okay, so what I left open was the question of how to deal with the gray concepts, in particular the purpose restrictions, and that's what I want to transition to next on formalizing and enforcing purpose restrictions. What we want to do is to give a semantics, a definition of not for and only for purpose restrictions that talk about information being used not for a purpose or only for a purpose. That's parametric in the purpose, meaning that should work for all purposes. And then to provide an audit algorithm for detecting violations based on that semantics. Let me try to give you the central idea with a simple example. Think about a setting in a hospital where a technician takes an X-ray and he either adds the X-ray to the medical record and ships over the record to a specialist for diagnosis. This interaction is guided by the policies, constrained by the privacy policy that medical records should be used only for diagnosis. So if he takes this path in the picture, then we expect the policy to be satisfied. His actions seem to be for the purpose of diagnosis. On the other hand, he could be evil. He could send over the record to a drug company because they gave him some money, and then the drug company might use that information for advertising or something like that. So if he takes this path above, this top branch of the picture, then we expect that this action was not for the purpose, right? So this simple example is a sanity check for whatever definition we come up with. We expect that if the technician took this path through the picture, then his actions respected the privacy policy, that his actions were for the purpose of diagnosis. If he takes this path, then we expect his actions to be not for this purpose. So here's one possible candidate definition. We are going to say that an action is for a purpose if it helps achieve a purpose, if it causes a purpose to be achieved. Now, according to this definition, these two actions are certainly for the purpose, because if they are a necessary element of a sufficient sequence for achieving the purpose, these two actions together help achieve the purpose. On the other hand, this one does not help achieve the purpose. So our simple sanity check is satisfied by this definition. Yes?
How do you work with the case that the person does take the correct path, they add the X-ray and they send the record for diagnosis, but then they also send another copy to, the drug company, for example?
Right. So that's why I said it's a necessary element of a sufficient sequence of actions for achieving the purpose. That additional action that you just talked about would be a redundant action, so that wouldn't satisfy the definition. So this is a simple definition based on causality. Good question. But even that is not good enough. And one of the reasons for that is it could be that the X-ray was added, but with some probability, the specialist failed to arrive at a diagnosis. With some probability, no diagnosis was achieved. Now, if you look at this, now these actions, according to the achieved purpose definition, are no longer for the purpose, and yet intuitively they seem like they should be for the purpose. So there is a mismatch between the definition and what our intuition might suggest. And the reason for that is what we should be capturing here is not that the purpose was actually achieved, but that the actions were done with the intention of achieving the purpose. And that notion of intention is missing from this definition. So here's how we modify the definition. We are going to say that at every choice point, the agent does the best possible, picks the best choice for achieving the purpose. So at this choice point, if he picks this path, then he definitely does not arrive at a diagnosis. If he picks this path, then the expected value that he will arrive at a diagnosis is positive. So he should pick this path given the choice. And this can be captured, this intuition can be captured through this thesis that says that an action is for a purpose if and only if that action is part of a plan for furthering the purpose. That is, what I mean by a plan is that at every choice point, he makes the best possible choice for furthering the purpose. And this is more than a play on words, because planning is something that we know how to formalize and deal with algorithmically using models like Markov decision processes, which is exactly what this picture is. This is a Markov decision process for those of you who are familiar with the formal model. And this gives us an algorithm for this thesis, then translates into an algorithm for detecting violations, where the audit algorithm now takes as input the policy, the purpose restriction policy, the auditee's behavior as recorded in an audit log, and a decision-making model, which shows what choices he had, which was this picture of Markov decision process. And then the algorithm can come back with an answer about, yes, the policy was obeyed or it was violated, and in some cases, it's going to be inconclusive. So in a little bit more detail, if you look inside this box of the algorithm, the audit algorithm, Here's the policy in our example that the medical record should be used only for treatment. The audit log records in this example that the top branch was taken where the technician just shipped over the record to a drug company for advertising or some other purpose other than treatment. And this was the decision-making model, which is this MDP. Now, the algorithm, what it's going to do is that it will solve the MDP, compute the optimal actions for each state, and check if the auditee actually made the best choices. And if the answer to that is no, then the policy implication is that the policy was violated. So that's the high-level idea behind this algorithm. The summary that I want to leave you with is that an action is for a purpose, according to our thesis, if and only if that action is part of a plan for furthering the purpose. That is, it always makes the best choice for furthering the purpose. And then the audit algorithm detects policy violations by checking if the observed behavior could have been produced by an optimal plan. And if the answer to that is no, then that's a violation of the policy. So here's how we have gone for something that's very gray and fuzzy, unclear what it means, to an operational definition that can be algorithmically checked. Okay, so that brings me to the end of this piece on healthcare privacy, where the two central algorithms was the reduce algorithm for checking the black and white concepts that does reasonably well on the HIPAA Privacy Rule, for example, and then this conceptual definition of what it means for an action to be only for a purpose, and an algorithm based on planning for automatically detecting violations of purpose restrictions. In the remaining time, I want to transition to web privacy. And as I transition to web privacy, we are also transitioning away from the setting where we are checking that people's actions inside organizations respect privacy to programs respecting privacy policies. The first paper that I want to touch on is going to appear a few months later at the IEEE Symposium on Security and Privacy. We call it Bootstrapping Privacy Compliance in a Big Data System. This is joint work with my student Shayak Sin, who did most of the work, and a bunch of people at Microsoft Research, most notably Saikat Guha. With him, Shayak worked last summer. So the setting here, we return to Bing. And the setting is that we want to check that the implementation of Bing respects the privacy promises that Bing makes on its web page. And the auditor in this setting, that's Shayak, has access to the source code. This is a person inside of Microsoft who has access to the source code and therefore can look at the source code, examine the source code, and try to ensure that it's respecting the privacy promises that they are making. Now, before we started working on this project, the way that Microsoft went about its privacy compliance, and this is not just specific to Microsoft, we have heard talks from Google and Facebook at various seminars at CMU over the last couple of years, and this is very similar to how these big data companies try to do privacy compliance. There is a legal team that crafts the privacy policy, and then there are meetings between the legal team and people who sit between the legal team and the software developers. At Microsoft, they call them privacy champions. Other companies have other names for these positions. And these guys try to interpret the policy that the legal team crafts and communicates that policy to developers who actually write the code, to product teams who are writing products related to, let's say, a search engine analytics or any other web service that these companies produce. And then there is an audit team that talks with everyone to try to ensure that this code respects the policy that the legal team is crafting. Now, there are several central challenges in this setting. One is that the policy tend to be ambiguous. Their meaning is unclear. It's not clear at all what this policy means, not clear enough for a developer to be able to write meaningful code. A second challenge is that there are these huge undocumented code bases and data sets. So inside of the data analytics pipeline inside of Bing, there are millions of lines of code, and they are not annotated with the kinds of information that tie back to the policy concepts. So there is a disconnect between this layer where the code is being written and this layer up here, which is crafting the privacy policy. Compliance then becomes a nightmare to show. The third challenge is, of course, one of scale. These are really large systems, and they're too large, way too large for manual audits to be meaningful, so we want some form of automation. So what we would like to do is have automated support for checking compliance to address the third problem, and then the first two challenges I will turn to give you a sense of how we help address. So I'm going to show you an example, try to explain this policy language called Legalease with an example. And that's all I'm going to do in today's talk due to constraints of time. So we return to our running example from the very first or second slide of the talk. And I'm showing you how it's expressed in Legalease. This is saying that we are going to deny the data type IP address to be used for the purpose of advertising, except if the IP address is truncated. This goes back to the policy that says full IP address or detailed location information will not be used for advertising. But if you truncate it, if you take off the last octet, let's say, then that's okay because now you're targeting a larger geographical area. That's the intuition that this policy is trying to capture. Yeah. Now this language has a clean syntax with layered allow-deny information flow rules with exceptions. What I mean by layered allow-deny rules with exceptions is exactly what this example is showing. We are going to say that certain type of information is denied for use for certain purposes, except if, and then there's this exception that's laying out an exceptional condition under which it could be used. And this layered language that Shayak came up with is particularly interesting because we have looked at other privacy regulations. Remember that I mentioned the full formalization of HIPAA Privacy Rule and the Gramm-Leach-Bliley Act, which we did a few years ago. Exceptions come up in a very prominent way in all of those examples as well, which provides at least some evidence in support of our belief that the mental model of how these policies are crafted higher up the chain, not by software developers, but by the legal privacy policy team, they think along these lines of deny, allow, layered through exceptions. The language has a precise semantics, so there is no ambiguity about what it means, what a certain policy means. And we have also done a usability study recognizing that the first order logic fragment that I showed you earlier in the talk is not something that today's software developers or lawyers will be able to work with. But this language is a lot more usable. It's much closer to how our target audience thinks. And an initial preliminary user study of Legalease inside of Microsoft with privacy champions whose job it is to do this work is quite promising. So a fragment of the Bing privacy policy, they were able to express in this language in about 15 minutes, and the majority of them got all the clauses right. The paper has additional details about the user study. The second challenge, so that's partly addressing the challenge of how do we come up with a language that could be used by the legal privacy team and the people who sit between the legal privacy team and the developers. The next challenge that I was mentioning it has to do with the fact that we have these huge undocumented code bases and data sets. So if you look inside the data analytics pipeline at Bing, then what it looks like is what this slide looks like. You have all these data sets and all these processes or programs that are operating on them. The programs are written in MapReduce-like languages in particular scope. And there is no sense of what these data sets are or what these jobs are trying to do. So our goal in designing Grok was to make some sense of what these data sets and what these programs are doing automatically. That is to annotate the code and data with the policy data types, with the kinds of data types that show up in the privacy policy. So to bridge the connection to make the connection between what the policy talks about and what the code is actually doing. So what we would like this picture to be ideally, instead of a jumbled mess of data sets and programs, is to say that, look, all these tables in the top row are really about names and ages and IP addresses and anonymized identifiers, the kinds of things that are governed by the policy. And that these lighter blue boxes, the programs, are new account creation programs and geo-IP lookup programs and a logging program and a program for checking fraud and so forth. And then we can begin to talk about data flows or information flows and checking whether, let's say, the hijack program, you see, is using name and address, an IP address, and maybe that's acceptable. But if some other program uses full IP address, that may not be according to our policy. Now, doing this labeling is difficult. The first step here is to notice that the sources, the absolute source nodes up here, can be named using a bunch of noisy analysis via variable name analysis. For example, we can look for regular expressions like email address to check whether a particular field is email address or not, or through developer annotations. If the developers were to annotate the nodes on this graph, then that would be great. But getting them to annotate 50 million nodes is not going to work, so we have to do something a little more clever. Once we have the source labels, though, we can propagate these labels via the data flow graph to get the labels on nodes further down in the data flow graph. So I want to give you an example of a policy violation for our example policy. Look at this data flow graph where full IP address is flowing to this reporting job, and the reporting job is part of the advertising pipeline, and that's a violation of our policy that says that full IP address cannot be used for advertising. So to fix that, we would have to put in a truncation job in between that truncates the IP address before passing it to the reporting job. Yeah? In this case, the state is truncated before it's passed to reporting, which then becomes compliant with the policy that does have an exception that allows truncated IP address to be used. Now, just to give you a sense of how we bootstrap these annotations, one simple idea, which works remarkably well for this application, is to pick the X% most frequently appearing column names and label them. So get developers to manually annotate the most frequently appearing column names, and then to propagate those labels using the Grok data flow graph. And that gives you this green curve, which shows on the x-axis the percentage of input that's manually labeled, and on the y-axis the percentage of input that gets labeled via this automated data flow propagation. Now, the most interesting algorithm which works in practice is that we pick the nodes which will label the most of the graph, and this turns out, in this case, the graph has so few sources that with only about 200 annotations, we can get high confidence labels on about 60% of the nodes, and that's the red curve on this picture. So this is providing some evidence that a small number of manual annotations is enough to get us off the ground for this particular data flow graph that's inside of the Bing pipeline. The other thing I want to give you a sense of is the scale of this system. Here are some numbers about the number of data flow graph nodes that are added each day to this pipeline. And if you look, it's about 50 million per day. These are some specific dates taken in October and November of last year, around the time we were writing up this paper. There are about 77,000 jobs that run each day by 7,000 entities, and that come from 300 functional groups. There's about 1.1 million unique lines of code, 21% of which changes on average daily, 46 million table schemas, and 32 million files. It's just the scale of the problem is big, so huge that manual audit is just out of the question. And this particular information flow analysis, which was implemented and is running now in the production system, takes about 30 minutes daily. So the result of all of this is a much more streamlined audit workflow between all these different parts of the privacy compliance team, where the legal team crafts the policy and encodes it in Legalease, which is then refined by the privacy champions who interpret the policy. On the other side, the developers who have written their code, the existing code that's already written through this code analysis and making use of developer annotations strategically, gives us the Grok data inventory with policy data types, which helps bridge, fill in enough information in the code about the policy data types that are referred to in the privacy policy. Now, this annotated code and the Legalease policy goes into the information flow checker, which then highlights potential violations to the audit team. The audit team then examines these potential violations manually. And if there is a real problem with the code, then they tell the developer to fix the code. And if it could also be a false positive because the data inventory, the Grok system, is not perfect, in which case there's feedback there to fix and update the Grok inventory. So this hugely streamlines the audit workflow inside of this kind of a company. Okay, so that's a short summary of this piece of work. In the remaining time, I want to transition to a different setting of information flow experiments, also for the web privacy setting. And in this setting now, the auditor is outside the system. So Shayag was inside of Microsoft, but auditors cannot always be inside. And we also want to be able to check or detect violations from the outside, especially in the setting of web tracking. So here it's a user who is interacting with Google, providing various search terms, some of which might be sensitive, indicative of things like race, and then they see some ads. And if sensitive search terms related to race and so forth affect the ads that they see, then that's an example of an information flow that's undesirable, that Google promises that they will not use this type of information to show ads, for example. Now, the interesting challenge here is that the analyst, the auditor, is on the outside. The Google's implementation is like a black box to them. This is a very different setting from the one in the last part of the talk, where Shayag was inside of Microsoft and could play with their code. Moreover, we have a bunch of confounding inputs because there are hundreds of millions of other users who are also interacting with Google, which might have an effect on the ads that this guy sees. I wanted to emphasize that the auditor is on the outside in this setting. So we want to do information flow detection in this black box setting, and that's what I refer to when I call them information flow experiments. Now, this is very similar to how experiments work in natural science. So if you think about trying to figure out whether a drug is fatal to bunnies, then the experimental group is given the drug, and a control group is given some placebo. At the same time, these bunnies are interacting with food and their place of residence and so forth. So those are the confounding inputs that we have to guard against. At the end of the day, we are interested in checking whether this treatment, the drug, causes death or not. And if a lot of bunnies die, then that might be evidence that is the case. In the information flow experiment is analogous, where we have a whole bunch of these, where we might have a whole bunch of these experimental inputs, and we might be interested in checking whether, if you indicate to Google that your race is black, you see a lot more arrested ads, and that was a study that was done by Latanya Sweeney last year. And if you're white, then you see looking for love ads, right? So this discrimination is something that people are concerned about. Now, one challenge with this picture is that we don't have, unlike bunnies, we don't have many, many different Googles to interact with. So instead, what we are going to try and do is create a whole bunch of instances of a browser and interact with Google. But we have to be careful now because these experimental units might interact with each other. And there is an analogy here with how between experimental science and information flow. We have, in experimental science, we have natural processes, biological processes, physical processes, and so forth. Information flow, we have the system in question, Google in our case. We might have a population of units that we are studying, like the bunnies, a subset of interactions in our case with Google. And the concept in experimental science that's closest to information flow is causation. And in fact, we have a technical result showing that a certain notion of probabilistic information flow coincides with the notion of causation as formalized by Julia Pearl. So that helps us because now we can start looking at ways of determining causation to determine information flow. So let me show you one result that indicates why this problem is, or some of the nuances of this problem. One thing to notice here is that I said, let's just replicate these browser instances, have a whole bunch of instances and use that instead of replicating Google because we don't have many different copies of Google. The first thing we observe is that browser instances are not independent. So this is an example in which these browsers, we are only running one copy of the browser on a machine, you see on these experiments, and as well as this one. Whereas in these experiments, we are running many different copies of the browser, many instances of the browser on the same machine. And on the y-axis, we are counting the number of unique ads. You'll see that the number of unique ads that are received by the browser when running single browser instances is significantly higher, it's statistically significant, than the number of unique ads you get when you run multiple instances of the browser. And this is indicating that we can't just assume that these different browser instances are independent. And that is relevant because that limits the kind of statistics we can use. Once you have independence between these experimental units, you can use a lot more. There are a whole bunch of other statistics you can use, but this is something that restricts the space of instances. So our idea was to use non-parametric tests, specifically a permutation test which does not require independence among browser instances. And one of the other reasons to use a non-parametric test is it does not require a model of Google. Yes, so Google has a very complicated internal algorithm that we don't want to make assumptions about. And if you want to use parametric tests, then we have to know something about that model. And there are some other experiments we did to provide evidence that Google has a particularly complicated model, and I have some additional slides about that. But in the interest of time, I'll not go into them today. So here's a simple experiment that we did showing that visiting car websites impacts ads. And it was on this, if you go towards the right side of this slide, those are the browser instances on which we convince Google that we are interested in cars by visiting a whole bunch of car websites. On the left side, these are the instances on which we did not visit the car websites. And on the y-axis are the number of car-related ads that we saw, and you see that the number of car-related ads is a lot higher on the right side of this picture on the slide than on the left side. And using the permutation test in our methodology, we were able to conclude with statistical significance that visiting car websites does impact ads. So what we have here is a rigorous methodology for information flow experiments that shows this technical connection between causality in the natural sciences and information flow as formalized via a form of probabilistic non-interference, an experimental design for causal determination, and significance testing with non-parametric test statistics, which is to take into account the fact that we don't have a model of Google, and moreover that the browser instances are not independent. And in ongoing work, we are replicating a bunch, we are trying to replicate and analyze a bunch of experiments previously conducted, but systematically using this methodology, including some very interesting work from Guha et al. A few years ago. It's the same Guha as the one with whom Shayak worked over the summer, Wilson, Tatar, and Sweeney. And also to conduct new large-scale experiments systematically and tool support for automating information flow experiments. So let me wrap up here by summarizing this research area where we are trying to formalize concepts that arise in privacy policies. Often these are, as you may have been convinced by now, imposing restrictions on how personal information flows. And then enforcing these policies using a combination of accountability mechanisms based on detection, blame assignment, audit, resource allocation, and punishments. And the two application domains where much of our activity has centered has been on healthcare privacy and more recently web privacy. So thank you very much, and I will take questions. Okay, let's thank the speaker. Yes. So especially the first part of the talk, you
highlighting what I would call explicit leaks, a nurse passing information out.
Yes.
Most of the concerns I've heard recently, and that frankly I face in some of our research, is not what I call explicit leaks, but are we collecting or are we leaking out enough information that someone else could then reassemble the personal information? And so how does that feed into this kind of work?
Yeah, so that's a very interesting question. Explicit leaks is what that work. You're absolutely right. It only addresses explicit leaks. Reassembly is a difficult question, and the technical community does not have a clean answer to that question. So I guess the short answer to that is I don't know, and neither does anyone else. The somewhat longer answer is that for a specific application domains, there is some progress. So in particular, I don't know how to do that with healthcare data or with court records, which are hugely problematic as they're moving online. But for statistics, there is some progress. So there are some settings in which what you're releasing are statistics, and there could be a concern that the statistics that you're releasing might be combined with other sources to learn additional information beyond what just that statistic releases. So there is some work on differential privacy and generalizations of it that try to address that question by providing a relative privacy guarantee, saying that the idea there is the database, consider two databases that are identical, except that your data is in one, not in the other. And the guarantee is that the statistic that is released does not change too much in a probabilistic sense, whether it's computed on the database with you on it or the database without you on it. And this has some nice properties like self-composition. So if you're only releasing differentially private data, then your privacy is no worse whether you are in the data set or not. That's about as far as we have gotten in this problem. It's inference control in general is a really hard problem. There are some impossibility results as well about that. So at some level, I guess another kind of answer to your question is that, at least from where I stand, trying to prevent information from leaking might increasingly become a losing battle. We have to try to better monitor how information is being used. And if those uses are problematic, then that's where the accountability regimes have to come in and detect and appropriately blame and punish. Any other questions? Okay, we should. Thank you very much.